Hello everyone, welcome to the linear elasticity course. In this video we're gonna continue the topic that we started in the previous meeting, which is the vector and tensor calculus, and today we're gonna focus on the operations on tensors. But before that, basically before we focus more on the tensor, let me go over very quick or give you a very quick summary of the points that we already covered in the previous meeting. We had introduced for the vector and the tensor, and we said that these are like like different parameters or different parameter that or physical quantities that describe a specific physical phenomena that we may experience in our life or we may use in different engineering application. In this course, we are interested in linear elasticity. So what does it mean, linear elasticity? It means that we are interested to figure out the behavior of, or the elastic behavior of linear elastic materials. And we are going to discuss this with details as we go through the course. But before we start and go deeply through the linear elasticity and continuum mechanics and these aspects, because basically we're going to deal with different parameters and different physical quantities, and we would like to describe these physical quantities. These physical quantities in general, it would be in the form of a vector or the form of a tensor. And this is what we introduce, and this is our interest actually, is to know how we can do different operations over vectors and tensors. And these operations basically that we're gonna set up and establish here through the first part of the course, we're gonna use them a lot through the course as we cover the different topics of the linear elasticity course. But anyway, in the previous meeting, we introduced what does it mean vector, what does it mean tensor, and we have discussed some simple operations over vectors. So let me give you a very quick summary just to remind you with the thing that we already covered in the previous meeting. First of all, we started that we distinguish between a scalar quantity and a vector quantity. We said that a scalar quantity like S, for example, let us assume that S is a scalar quantity here, like S. We said that this scalar quantity would be you just can use any letter like S, R, Q, whatever it is, just a scalar quantity. Assume that this is a scalar quantity, S scalar quantity. So for any scalar quantity, basically, it's just a scalar. Like we give example to this case, like you'd have S equals 5 or 6 or 7 or -1, or even it would be like 3x squared y, as we are going to discuss in today's lecture. But anyway, anything that does not depend on a direction, this is a scalar quantity, and you should know this thing from the physics class even. So the scalar simply is just a value, it has no direction, we don't care about its direction. The other option that we have basically, and in the meanwhile also we said that the scalar quantity, it is a zero in terms of the tensor notation. We said that this is zero order tensor. Why? It does not require a direction. But the first order tensor, which is the vector V, we said that vector, it would be any letter like A, B, C, whatever it is. So V, but it should be uppercase just to distinguish between the scalar quantity and the vector quantity. So this is a vector. And we said that the vector, basically, it should be a first order tensor, right? And we said that generally the vector V, we can write this one in a compact form, like we can say that it would be like VI delta I, where we define the VI, these are the components, VI, these are the components of the vector, while the delta I, this is the unit vector. So the delta I itself, it is a vector, but the delta VI, it is a component, and this what gives the magnitude. This is, like these are the values. You could say that these components are the values of the vector. As you know, even from mathematics, like the vector, it has 3 different components, the X component, Y component, and Z component, right, in 3 dimensions. So the Vxi here, it would be x, y, and z. So Vx stands for the x component of this vector, and Vy, it stands for the y component of the vector, Vz stands for the z component of the vector. And as we discussed before, at these components, basically, these are just values. And the thing that we define with the direction is the unit vector itself. The unit vector, for example, if I say delta x, this indicates that this is the x direction. This is the direction parallel to x. Delta y, this is the direction that is parallel to y. Delta z, direction parallel to z, and so on. So that's why the vector, it is a vector quantity that requires two things. Require magnitude and direction to be fully defined. The magnitude, it has been defined by the different values, the different components of the vector, which are Vi, but the vector direction, which is through the delta I. This is the compact form, and we said that is fine to use any index. This I is known as the index, and we said that is fine to use any index. For example, that is fine if I write, if you can write here. Let us just mark this one and mark this point. So let us assume, for example, we can write Vj delta j. This vector is typically the same like this vector is typically the same original vector V. So this is the vector. We said that we can write the vector in this form, but there is no need to write. Since you aren't going to add any indices, this indicates that you are talking about the vector itself. But here, you are representing the vector in terms of its components, but in a compact form. How about if you decided to expand it over x, y, and z? So we're gonna have here Vx, where this Vx, this is the x component of the vector, delta x plus the Vy delta y plus Vz delta z. Again, as we agreed, these deltas, these are the unit vectors along x and y and z, and Vx, Vy, Vz, these are the vector components as we discussed the previous meeting. Make sense? So this is how we represent the vector, and again, the vector is a first order tensor. And you should understand that the vector, it has three components only. One component parallel to x, another component that is parallel to y, another component that is parallel to z, like a position vector, velocity vector, acceleration vector. All of these are just, all of these physical quantities, which are position, displacement, velocity, acceleration. These are physical phenomena. These are physical quantities that describe specific physical phenomena that describe the motion of objects in this life, right? Generally. So these physical quantities, we are using them a lot in engineering, in mathematics, in any field of science, whatever it is, right? Especially engineering in different engineering application. So these physical quantities describe something in reality. This something, it should, to be fully defined, require magnitude and direction, and it should be described using a vector, right? In addition to the vector, as we discussed in the previous meeting, we may have more. So the vector is just first order tensor. We may have a tensor that would be second order tensor, and so on. So the tensor, it is like multiplication of two vectors or three vectors together. Like you combine, and instead of having just one vector, you're gonna combine some multiple vectors together to end up with a tensor, which is gonna be in the form like a matrix, right? So you should understand that the tensor is something like the vector. Tensor is something that describes a specific physical quantity that would be used for describing a specific physical phenomena in reality, as typically the same like the vector, right? So the tensor, basically, and we said that we're gonna give it these letter, which are the Greek letter, like tau, for example. So this is a tensor. And we said that the tensor, it would be second order tensor, third order tensor, and so on. So we do have zero order tensor, this is the scalar quantity. We do have the first order tensor, this is the vector quantity. But any higher orders will be represent a tensor in general. Like, for example, and this is what we basically gonna depend on a lot through the linear elasticity class, is the second order tensor. So let us assume that we do have a second order tensor. So, and as we discussed in the previous meeting, the second order tensor has 9 independent components, as I'm gonna show you. So generally, the second order tensor as tau, we can write this tensor as tau ij, where the tau ij, this stands for the components of this tensor, like what we did for the vector. We have vi, these are the components of the vector, delta I, this is the unit vector. So the same thing for the tensor, we have tau ij, which stands for the components of this vector, delta I, delta j. So these are two unit vectors multiplied, delta I times delta j. This gives a tensor. So if you multiply any two unit vectors times multiplied together, this gonna give a tensor. So if you have three delta I, like delta I times delta j times delta k, this indicate a tensor, but this tensor would be third order tensor, higher order tensor, and so on. So what is a big difference between a vector and a tensor? The vector, it has only one delta, which indicate that this delta, because this delta is gonna be like delta x, delta y, delta z, it has only three components. But here we do have delta I and delta j. So it means that for the case that I is already x, we do have the option that j it would be x or y or z. So for just one value of I, we do have three corresponding value for j. So 3 by 3 gives 9 components. So that's why we said that for the second order tensor, and we even wrote all the components of these 9 components in the previous meeting for a tensor. So this is generally the expression of a tensor, and we said that is fine to use any indices. That is fine to use I, j, k, whatever the indices itself, the index itself, it doesn't matter. Anyway, this is a tensor with two unit vectors already multiplied together as shown here. So this is basically the tensor, and we can write this tensor in the tensorial form like as we agreed the previous meeting. Like we can assume here we do have, this is the column x, column y, column z, and we do have the row x, the row y, and the row z. So the components will be in this case where, as we mentioned the last time, the previous meeting, that the I here stands for the row number. This is the row number. This stands for the row number. But the j stands for the column number. So what does it mean? It means that here, if I'm seeking the component that is located at x location, like row number x and row number x as well, so the column x, so column row x, column x, so it means that I'm talking about this component, and this component in this case, x is gonna take I is gonna take x, j is gonna take x. It means that I will be x, so tau x, this is the component in the x location. Here I'm talking about the component in the x, y location. Remember that the row should come first for the tensor. So the row first, I'm still working in the x row with the column y. Here I should have the xz. Then here now I'm moving to another row which is y. So I'm gonna have tau yx. Here I'm gonna have the tau y. In this case we're gonna have the tau yz. Here we're gonna have the zx because the row is gonna be z. The column is gonna be x. So tau zy and the tau zz. So these are the 9 independent components of a tensor, and this is what we introduced the previous meeting. Also, then we move directly to the different operation that we would consider for vectors, and especially for vector, and we consider just the simple operations. We started even with the simplest operation ever, which would be the addition or the subtraction of two vectors. Let us assume that we do have a and b. These are two different vectors, and we are interested in just summing, just to calculate, find the sum of these two vectors. So we said that it is better to write this one in terms of its components. So this is the tensor, the vector a. Its component in the component form will be ai delta I, where I just any index that is gonna take x, y, and z. Then we are going to sum or subtract whatever the operation is for the other vector, which is delta bi, which is bi delta I. As we agreed, since we are using different terms, this is one term, then there is another term. Why this is a term and this is a term? Because there is plus or minus in between. If there is plus, the addition or the subtraction, this gives multiple terms or different terms. But the multiplication, this gives the same term. We're still working with the same term. We agreed the previous meeting, in case that you're still working in the same term, you cannot, or we are not allowed to use the same index multiple times in the same term. Again, we are not allowed. It is not possible. According to the tensor and vector calculus, we shouldn't use, we are not allowed to use the same index in the same term. So for example, in this term, I used I. Then I move to another term. If when you move to the other term, use, it is better. It is advised to use the same indices that you used in the previous term. But if you're still working with the same term, we shouldn't use the same index. The index should be used once. Then when we move to another term, we can repeat the index or use the same index one more time. Make sense? So then we can just add, we can do the operation like AI, because delta I, we can consider the delta I like a common factor of this simple equation, right? So we can have del AI plus or minus, depending on the operation, PI, and this gonna give us delta I as a common factor. So what does it mean? The addition or subtraction of two vectors at the end is gonna give us a vector as well, right? And even we can write this one in the expanded form if we would like to write in expanded form. So we can have like the AX plus or minus the BX delta X, because you're just gonna consider the I as X, plus the AY plus or minus the BY delta Y, plus the AZ plus or minus the BZ delta Z. So what does it mean this? This means if we have two vectors and we would like to sum them or subtract, like the summation or the addition or subtraction of these two vectors, so your objective is just to add or subtract the X component, add, subtract the Y component, add, subtract the Z component. This is going to give us the X component of the resulted or the vector, because the sum of two vectors is going to give us a vector. So what is the shape of this vector? Is going to be sum the X component. This is going to give you the X component of the resulted vector, and the Y component of the resulted vector, it should be the sum of the Y components. The sum of the Z component, this is going to give us the Z component of the resulted vector. Okay, so this is very simple how we can sum vectors according to the vector and tensor calculus. Make sense? To the scalar, the multiplication of scalar with a vector. Like let us assume that we do have a scalar quantity like S times V, where V is just a vector. This is scalar and this is vector. So the multiplication of a scalar times vector, it is very simple. You're just gonna multiply times the scalar. Like we're gonna have S VI delta I, this is the expanded form. This is the vector in terms of its components, but in the compact form, equals, so that is fine to do the multiplication of the scalar like 5. You multiply times a number, right? So it's going to be like S times VI, and you're going to have the components, the unit vector as delta I. So the expanded form of this operation, actually, this is going to be the SVX, you're going to multiply the same number times the X component of the vector, the delta X, plus the SVY delta Y, plus the SVZ delta Z. So these are the three components of a vector. As we agreed, the vector gives three components. Then we discussed another operation, which is very important operation, which is the dot product of two vectors. Like we do have a vector A times, it is dot product vector B. So the dot product basically, and this is one of the things that you should consider. We said that in case that you'd have a vector and there is another vector, the dot product of two vectors gives a scalar quantity. You should understand this point. The dot product of two vectors gives scalar quantity. So we are expecting a scalar quantity here. So how, basically, let us write the A vector in terms of its components. So it's going to be AI delta I dot. When we are going to write the B vector in terms of its component, we should use a different index. Why a different index? Because we're still working in the same term. We're still in the same term here. We didn't move to another term. To move to another term, to consider this is like a term, and this is another term, there should be plus or minus here. But this operation, it is dot product. This is not addition or subtraction, so we're still working with the same term, so we have to use the same different index. The same index, it should be used once. So I already used I index with A vector. For B vector, you should use a different index, whatever it is. You can use I, J, you can use J here and I there, K, M, whatever the two indices are, it doesn't matter. So then, basically, for the dot product, we just do the multiplication of the component. This AI, this is the components of the A vector, these are the components of the B vector, so we're gonna multiply AI times Bj, multiplication, conventional multiplication. So these are the components will be multiplied, but how about the unit vector? We're gonna do the operation itself over the unit vector as delta I dot delta J. We agreed in the previous meeting that you should memorize this relation, that the dot product of delta I dot delta J, this gives delta Ij, which is known as the canonical delta. What is the canonical delta? I'm gonna write this one here. Delta Ij, also, this is one of the important operations that you should, or parameter that you should understand, that delta Ij, it should be either 1 or 0. When it should be 1, in case that I equals J, but it should be 0 in case that I is not equal to J. Remember that I and J, these are indices. It means that the index I, it would be X, Y, or J, or Z, the same thing for J. For the instant that X and J, I and J, they do have the same index, like X and X, Y and Y, Z and Z. So delta Ij, the canonical delta is 1. But in case that I is not equal to J, it means that by definition, delta Ij should be 0, right? So simply, we're gonna say that this is for the delta Ij. So I'm gonna say that I can write AI Bj. This multiplication gives us delta Ij. What does it mean, delta Ij? This is the canonical delta. How about if we would like to get rid of the delta Ij? To get rid of the delta Ij, you should use the same index for both I and J, because this delta Ij, it uses I and J. So for both I and J, I should use the same index. So this same index, it would be I, it would be J, it would be any other index, it's up to you. So for example, let us assume that we are going to use I for both I and J indices. So the AI will be I, and the Bj should be Bi. Why? Because I decided to use I for both indices I and J. So, and then I'm going to get rid of the delta Ij. As you can see, we're gonna end up with this term. This term has no deltas. There is no deltas here, right? So what does it mean? It is not a vector. It is not a tensor. The thing that defines a vector is delta. The thing that defines a tensor is 2 deltas or 3 deltas and so on, right? So here we don't have any deltas. It means that we do have 0 order tensor. There is no delta, it means 0 order tensor. A 0 order tensor, as we discussed above, it is a scalar quantity. So this is a scalar quantity. So the dot product of two vectors gives a scalar quantity, which is going to be AIBI. The expanded form, simply, if we consider I as X, so it's going to be BX, AXBX. If I is going to be Y, so it's going to be AY by plus AZBZ. Why we are considering like X plus Y plus Z? Because we said that this I is a dummy index in this case. Why it is a dummy index? What does it mean, a dummy index? As we discussed, dummy index, it means that this is a repeated index. When we do have an index that is repeated within the same term, you have to repeat, you have to sum. Like you consider this index X once plus Y once plus Z once another time. So this is going to give us end up with 3 terms. But these 3 terms will be summed together. When we sum together, we're going to end up with only 1 term as a result as a scalar. The scalar is just 1 component, as we discussed above. Make sense? So this is for the dot product. Also, we discussed the cross product of two vectors. This is also one of the important operation that would be done over vector, the cross product of two vectors like vector A cross B, For the vector A, if we decided to write this one in terms of its component in the compact form, so it's going to be AI delta I cross the BJ delta J. Here we have to use a different index. Why? We're still working on the same term. So if we did it basically, this is going to give us AI BJ. We said that for this case, the component should be multiplied together, no worries, AI times BJ, and it doesn't matter which one comes first. That is fine if we said BJ, AI, that is fine, it's still the same. Like you multiply 2 times 5 equals 5 times 2, it doesn't matter. But the operation it should be done over the unit vector, but the arrangement of this operation is a big deal. For example, delta I cross delta J is not equal to delta J cross delta I. Here we are working over vectors, but these just numbers. So we don't care which one comes first, right? But here we have to care, right? So if you remember also from the previous meeting, we agreed that you have to memorize this relation, that the delta I cross delta J, this gives us the permutation parameter, which is epsilon ijk delta k. And so ij, since we already have here ij, so I have to use the same index, ij, but you're gonna add an additional index. But make sure that this index, you didn't use it before. We don't have any case here, so you're gonna add k delta k. If you decided to use m, so it's gonna be delta m, and so on. Any other index, whatever it is, but this index shouldn't be used before, right? So, and if you remember some of the characteristics of this permutation parameter, like the epsilon ijk, it has 3 different possibilities. It would be either 1 or -1, or it would be 0. When it should be 1, we said that the condition for the permutation tensor to be 1, that the I and the J and the K should come in the same order as shown here. Like we do have I, then J, then K. So for example, if I decided to write like epsilon x, y, z, so this is in the same order. So I'm having x, then y, then k. So the value of this epsilon, it should be 1. Then we said that if we messed up with any of the arrangement of this order with any way, we're gonna end up with a -1. So for example, let us assume that you do have J, then I, then K. So this is not the same order that is already shown here. We have to have like I, then J, then K, then I again, then J, then K, and so on. But here we do have, in this case, we do have J, then I, then K, then we are going to start again from J. This is not the exact order that already given for the epsilon, so it's gonna take a negative sign, right? But the condition for these two is that none of these indices is repeated. It means there is no XX, there is no YY, there is no ZZ. But if there is something repeated, like for example, in case that I equals J for some reason, or J equals K, or I equals K, for this case, this term should be 0, this epsilon should be 0. So these are the properties of this canonical delta. So if we decided to use this one in this case, so what we're gonna do, basically, we're gonna have AI, BJ, then we end up with epsilon ijk delta k. Make sense? We said that is fine even to write this epsilon, start with the epsilon, then anyway, these 3 components, these are just like values, because this epsilon, it would be either 1, 0, or -1. So the arrangement of these 3 terms, it doesn't matter which comes first, which comes second, it doesn't matter. We can even move this epsilon in the start, it doesn't matter the arrangement of this epsilon. Make sense? How about if we decided to get rid of the epsilon, the permutation parameter? We said that we can do it, but we're gonna split this one over 2 different terms. Like we're gonna end up, this is the equivalent form without of delta k. We're just gonna carry on the delta k as a common factor, but we're gonna have here the AI, BJ, negative the AJBI. Just switch the indices between the A and the B, because when we switch, we already changing the order of the IJK. It means that we should end up with a -1 for the epsilon and negative in case that we're sticking to the same order. So that's why this term is multiplied times +1, but this one is multiplied times -1. So that's why we end up with these two terms, and this is basically the cross product of two vectors. And as you can see, the cross product gives a vector because we do have delta k. This is first order vector, so we're gonna end up here with a vector. It gives a vector at the end. Make sense? So this is for the cross product. As I said, this gives vector in this case. Then we moved next to the so these are the operations that basically that we covered in the previous meeting for operations over vectors and the this simple operation and the scalar, and we just introduced for the tensor. Now in this lecture, basically the interest is to introduce more or discuss more the operation that would be done over tensors. But before we proceed, basically, let us consider these important operations over the unit vector. So again, what is the unit vector? This is the delta itself. The delta that we introduced there, up there, this is the unit vector. So let us, like for example, some of the operations that we covered so far over the unit vector are the dot product of two unit vectors. Like delta I dot delta j, we said that this gives us delta ij, which is the canonical delta. And the other operation is the cross product of two unit vector like delta I cross delta j. This gives us the permutation permutation parameter add. But anyway, it's gonna give us a vector because this is gonna give us the permutation vector. Epsilon ij k delta k, right? So now, how about, is there any other operation that we can do over unit vector? Yes, and this will introduce us to the tensor concept basically, right? So now let us move to the operations that we can do over unit, some important operations over unit vectors. And let us start here, and basically we already discussed one. I'm gonna add the two operations that we discussed before for up here. So we said that the delta I dot delta j, this gives us the delta ij, agree? This is one operation. The second operation is that the delta I cross the delta j, this gives the epsilon ij k delta k. You have to use a different index than the ij, but you have to stick to the same indices here, like ij, so you should use ij, kl, so you should use kl, then m delta m, and so on. Make sense? So we already discussed these two operations. Now let us consider this double dot product. So this is this operation in case that we do have these two double dots. This indicates that we do have double dot product of this unit vector. Like we do have delta I, delta j, then there is double dot here in between, and we do have then another two unit vectors, delta k and delta l. So this double dot product, it can be split into two dot products. It can be split into two dot products. How? Basically, you're gonna do the dot product of these two terms, these two unit vectors, and then you're gonna consider the dot product of the other over the other two unit vectors. Make sense? Like you're gonna have delta j dot delta k, then times the delta I dot delta l. Make sense? Like you're gonna consider 2 times 2, but it goes in this way. Like we gonna pick the dot product of these narrow terms or closed terms and these far terms. So we're gonna end up with delta j dot delta k, delta I dot delta l. What is delta j dot delta k? We said that this is gonna give us a canonical delta, which is gonna be delta jk, because we are using delta j dot delta k. So this is gonna give us this term, gives us the delta jk automatically. How about this term? This is gonna give us the delta il. So we're gonna end up at the end with delta jk delta il, and this is like the multiplication of two canonical deltas. Make sense? So this is also one of the important operations that we should understand. Basically, you shouldn't memorize. The only two operations that you have to memorize all the time, these two operations on the top here, that the delta I dot delta J equals delta Ij and the cross product. But for the double dot, you should understand that we're gonna split it into two conventional single dot product. This is known as the single dot product, but this one is double dot product, as we are going to discuss later. But anyway, this double dot, it can be split into the multiplication of two single dot operations, as we did here. How about if we have only one single dot in this case? So this single dot, it should be done over the two vectors that they are close together. Like this dot is confined between delta J and delta K. So the operation, it should be done over the delta J dot delta K. It means that you're going to assume that there is a parenthesis here, and you're just going to carry on the delta I as it is. And it doesn't matter even where is the location of the delta I, it can be moved outside on the right or outside the parentheses on the left. It doesn't matter where is the location of delta I. But anyway, for this one, it means that we are going to do the operation just over delta J delta K, and delta J dot delta K gives delta JK, which is the canonical delta, but this is a vector. So this operation, remember that this dot product gives us scalar. This is a scalar quantity. There is no deltas here. This delta is delta, which is the canonical delta, but I'm talking about a unit vector. There is no unit vectors here. There is no delta I, there is no delta J, and so on. But here we do have delta I, so this is a vector. This quantity will be a vector. Make sense? How about this case? How about if we just move this delta, this operation to be between I and J? It's going to be the same. So it means that the operation should be done over the delta I and delta J, and the delta K, you're just going to carry on the delta K as it is. Make sense? So what does it mean? It means that I'm going to have delta I dot delta J, which is going to give us the delta Ij, then we're going to have the delta K as a vector. So we're going to end up as well with a vector quantity. How about this operation? This is a single. What is the difference between this operation and this operation? This is a double dot product, but this is single dot product. How about if we have a single dot product? It should be done over these two unit vector, but the delta L, delta I, we're gonna carry on them on as we move with the steps. So what does it mean? It means that you're just gonna do the operation itself over the delta K, delta J, and delta K only. So it's gonna be in this form, and the delta J, delta K gives delta JK, and then you just gotta carry on the delta I, delta L. So we're gonna end up with a tensor. This is second order tensor. Why? This is first order tensor. It has only one vector, unit vector. This is first order tensor, which is a vector because it has only one vector. There is no vectors here, so this is zero order tensor. But here we do have second order tensor. We do have delta I and delta L. Make sense? How about the cross product of these two vectors, and we do have the delta I. So this cross product, again, it's gonna be done just over these two brackets. I'm sorry, these two unit vectors, and we have to add two parentheses in this case. It means that the operation is gonna be done over just delta J and delta K. And you're just gonna carry on the delta I. So we're gonna carry on the delta I as it is. The operation, it should be done over the J and the K. If we did it as we agreed before, that is fine to get rid of the summation here. We didn't add the summation in the lecture, and we can consider or use the concept of the dummy index. It means that we are gonna have a repeated index. So in this case, if you are using the dummy index, there is no need to write the summation here. So anyway, this term bear this relation here. As I told you, these are the two important relations or operations over the unit vector that you have to memorize all the time. The delta I cross delta J gives epsilon Ij K delta K. So how about if we do have delta J cross delta K? So this should give us the epsilon JK Like, and you have to use any other index that you didn't use before. We used the I, we used the J and the K, so I can use M, for example, or L. Let us use L like what he did, basically delta L. So we're gonna end up with epsilon J K L delta L, which is gonna be typically the same, epsilon J K L delta I. You're just gonna carry on the delta I as it is, then delta L. But the order of delta I should come first, then delta L, because this is going to give us the tensor, and also this is going to be a second order tensor as given here. How about this case? Now the operation, it should be done. The operation, it should be done over this term, okay, which is delta I cross delta J. Make sense? So the operation, it should be done over this term. Okay, let me check something here because yes, okay, so this operation should be done over these two terms, delta I cross delta J. So, and the delta I cross delta J, this gives us, again, we're gonna get rid of this sum. This is gonna give us the epsilon I J. We already use K, so let us use any other index like L, delta L. So we're gonna end up with epsilon I J. This one, it should be L here. This should be L delta L delta K. Okay, this is just a correction. This is a typo in the textbook, so it should be L, because we already used here, we are doing for delta I cross delta J, so it should be epsilon I J L delta L, I J L delta L and delta K. You're just gonna carry on the delta K as it is. So this, it is a common known typo for this textbook of the transport phenomena in the appendix, which is this canonical data. It's just a typo, it is not a mistake or something. Okay, so anyway, this is gonna give us a tensor. Make sense? So these are some of the important operations that should be considered over the unit vector, and we're gonna use them a lot. So as you can see, there are some of the operations over the unit vector that is gonna give us a scalar quantity. There are some other operations that gives vector quantity. There are some other operations that gives tensors, right? And what distinguishes scalar from vector from tensor is the deltas itself. Do we have deltas or not? If we don't have any deltas, it means if we don't have any unit vector in the final result, it means that we're going to end up with a scalar quantity, zero order tensor. If we have only one delta as a unit vector, so it means that this indicates that we do have a vector quantity as a first order tensor, second order tensor or higher, basically. But as I mentioned, the higher order tensor, which are higher than second order tensor, we were not gonna cover this one in the linear elasticity class, except at the end of the class when I'm going to introduce to you the non-classical mechanics. And in this case, we may experience some tensors which are like third order tensors, especially the third order tensor. Make sense? So these are for these operations over the unit vector. Now let us move to the operation that we could do over the tensor themselves. So let us start with this important notice here, that the multiplication of two vectors, the multiplications of two vectors gives a tensor or a dyadic. We said that which tensor, because the tensor it would be second order tensor, third order, no, the multiplication of two vectors gives a dyadic which is a second order tensor. It means that it's going to give us a second order tensor at the end. This is the multiplication of two vectors. So let us prove this point. So what does it mean? It means that let us assume that we do have a vector A and there is another vector B. We didn't consider this operation before. What we covered the multiplication, the dot product, like we have a dot here, or cross product of two vectors, the multiplication of a scalar times vector, and so on. But here we are talking about the multiplication. It is not a product like cross product or dot product. We are talking about the multiplication, direct multiplication of two vectors A and B. This is going to end up with a tensor at the end. Let us prove it. So let us do it as we usually do. So let us write the vector A in terms of its component. So it's going to be AI delta I. Make sense? Times, this is a direct, there is no specific operation, there is a direct multiplication. How about the vector B? So it's going to be Bj delta J. Why we are using a different index? Because we're still working in the same term. Now, we can multiply AI Bj as multiplication, and we agreed that it doesn't matter which comes first, right? Bj, AI, or AI Bj doesn't matter. But it's gonna be a big deal, the order of the delta I and the delta J. The unit vector is a big deal. Their arrangement, which come first, it is a big deal to us, right? So we do have here delta I first, then delta J, so we're gonna end up with delta I, delta J. There is no specific operation over delta I times delta J. This automatically gives a tensor, as we discussed above, right? We discussed here that in case that you have two deltas multiplied together, the multiplication of two deltas, because this is a vector and this is another vector, this automatically gives a tensor. So this is the form of a tensor. What we end up here with is a tensor. And this tensor, these are the row components, or this I indicate the row, this J indicate the column of this tensor. So we're gonna end up with a tensor here. This is gonna be tensor. Make sense? So this is the compact form of the tensor. How about if I ask you to write this tensor in the expanded form, like a tensor, like in this way? We can write this one in the tensorial form, in this case. So we're gonna have, as we did in the tensor in the beginning of this video, when we did summary to the previous meeting's topic. So we're gonna have here X column, the Y column, the Z column, then the X row, the Y row, and the Z row. Agree? So what is the index here? Remember that the I refers to the row number. So this is, if we are working over this row, it means that I is gonna be X. Here I is gonna be Y. Here I is gonna be Z. But this one, if we are talking over this column, this is gonna give us J. So the J equals X, J equals Y, J equals Z. Make sense? So now let us talk about this component. What should be written here? According to this component, if we did intersection here, we are intersecting the X with the X. So this is the XX component. So what does it mean? It means that the AI, it should be X, and the Bj, the J, it should be X as well. So this is gonna give us AX, BX. But how about this component? This component, it should be, the X, it should be, the I, it should be X, but the J should be Y. So we're gonna end up with AX, BY. How about this one? Intuitively is gonna be AX, BJ, because here the column there is J, which is Z. But how about this one? Here the row, it is Y, so we're gonna have AY, but the column, it is X. The row, it is Y, the column, it is Y. The row, it is Y, but the column, it is Z. Here the column, the row, it is Z, but the column, it is X. The row is Z, but the column is Y. The row is Z, but the column is Z. So these are the components. We're gonna end up with a tensor of 9 independent components. So generally, in case that we do have components, in case that we do have two vectors, or in general, the multiplication of any two vectors gives a tensor with 9 independent components. And this is the compact form of this tensor, and this is the X, or the tensorial form of the tensor itself. Or even we can expand it. We can expand it like one single equation, as I'm gonna show you with this unit tensor. Okay. What is a unit tensor? This is another point that should be considered. A unit tensor, it means which is the unity tensor, or the unity matrix that we have covered before, like many times. The instructor for the math in the mathematics class, for example, we had experienced this tensor, like this one, for example. So this is the common unity tensor, or the unit tensor. This is the unit tensor. right? So how we can write this unit tensor in terms of the tensor notation? So we're gonna basically give it a symbol like I. We can use a symbol to this tensor like I, or just delta. It doesn't matter how we are going to give it a name, but let us consider I or delta, which is the unit tensor. This unit tensor is going to be written as delta ij. These are the component, which is the canonical delta, delta I, delta j. Remember that since we do have like delta I, delta j, delta k, delta m, any two deltas multiplied together, this gives us a tensor. Anyway, and the components of this tensor are the delta ij, which are the canonical delta. And if you remember that the canonical delta, it would be either 0 or 1. 1 in case, under only one condition, that I and j should be the same index, but in case that I and j, they are different indices, so it means that this should be 0. So if I ask you to write this tensor in an expanded form, what is the expanded form of this tensor? So we're gonna say that this tensor, it should be expanded over 9 components. Over 9 components. So let us write the 9 components of this tensor here. So we're gonna start here with the delta xx, delta x, delta x. Agree? This is the xx component. Plus, if you just follow the tensor up there here, then we're gonna move to the second component, which it should be the yx. So we're gonna have here, which it should be the xy. So we're gonna have here the delta xy, delta, the row it should be x, but the column it should be y, plus the delta xz, the row it should be x, but the column it should be z. So these three components, these three terms represent the first row in this tensor. How about the second row? Do the same, plus. Now I'm gonna move to the yx, delta y, the row is y, but the column there is x, plus delta yy, delta y, delta y, plus the delta yz, delta y, delta z. Make sense? Row is y, but the column it is z or y or x. How about the third row? The third row, now the I, it should be, so it should be z. 1x, once it's gonna be x, so it's gonna be delta z, delta x, plus the delta zy, delta y, I'm sorry, delta z, delta y, plus the delta zz, delta z, delta z. Make sense? If we're gonna look to all of these components of the unit tensor, so all of them are the canonical delta. Which one of these canonical deltas is 1? Which one is 0? Any canonical delta with the same index, it should be 1. But if we do have different indices, it should be 0. Make sense? According to the definition of the canonical delta. So what does it mean? It means that this term, it should be 0. This term will be 0. This term as well will be 0. Right? They do have different indices. This term will be 0. 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 So we're just going to end up with 3 terms, which are the diagonal components of this tensor, right? So we're just going to end up with these 3 terms, which are the equals. The delta xx, delta x, delta x, plus the delta yy, delta y, delta y, plus the delta zz, delta z, delta z. And you should understand that delta zz, delta yy, delta, they are just 1, right? Their values are just 1. So that is fine even if you just type delta xx, I'm sorry, delta x, delta x, plus delta y, plus delta z, delta z. Why? Because these coefficients, intuitively, they should be 1. And this is basically what matches with the tensorial form that we commonly knew about the unity tensor or the unity matrix somehow, that the x component, xx component, it should be 1, but any off diagonal, it means that the diagonal, it should be 1. These are the diagonal component, but the off diagonal component should be zeros. This was explained that this unity tensor. Like these are these components over the diagonal, these commonly known as the diagonal components. These are the diagonal components. These are the diagonal, right? And the other components, which are these ones, and these ones should be zeros, right? These are the off diagonal. These are the off diagonal component. Okay, so this is for the unit tensor. So now we said that the multiplication of two vectors gives a tensor. Then we discussed the unit tensor. Now let us move to the addition, some of the operations that we can do over the tensors, starting with the addition of two tensors. So how about if we do have one tensor, like, so let us move here to the addition. Like, let us assume that we do have a tensor as sigma. This is a sigma tensor, one tensor as second order tensor plus tau. And remember that when we add or subtract any two tensors, basically, these two tensors should be of the same order. Should be of the same order. It means that both should be second order tensor or third order tensor or fourth order tensor. But different orders, there is no physical meaning. We didn't experience a physical system that would give relation or would be described by an equation or a relation that require the addition or subtraction of two tensors of different orders. Okay, but anyway, we do have sigma plus tau. So if we decided to write the sigma tensor in terms of its components, so it's going to be sigma ij, for example, delta I delta j. Plus it means that we have moved to another term. So that is fine. It means it is better, or you could say that we have to use the same indices with the same order that we used them in the previous term. Okay, so to have some kind of consistency in the tensor notation. So anyway, so we're gonna have here the tau ij, then delta I delta j. These are the two tensors, but in terms of their components somehow. So as you can see in these two terms that we do have the delta I delta j, these are two common unit vectors that we can take them as a common factor. So we're gonna say that we're gonna end up with the sigma ij plus the tau ij. This is gonna give us the delta I delta j as a common factor here. So what does it mean? It means that the addition of two tensors gives another tensor. Simply, you're just gonna add or subtract, the same thing for the subtraction, by the way. You're just gonna add or subtract the components, every component and its corresponding component of the other tensor. They should be summed together or added together to end up with the addition or subtraction of two tensors. Make sense? The next operation is multiplication of a tensor by a scalar, which is also very simple operation and intuitive one. Like if in case that you do have s as a scalar quantity and we do have tau, which is a tensor. In this case, the s times, so the s, there is no components for the s, it's just a scalar quantity. But how about the tau? It can be expanded or written in its component form as tau ij delta I delta j. So simply, what we have to do, we can simply multiply all the components of the tensor, times s, where s is just a number, and just get on the delta I delta j. It means that you're just gonna end up with typically the same tensor, but instead you're just gonna scale up s. This is like a scaling operation. Okay, so this is, you're just gonna multiply all the components of this tensor times the s, which is just the scalar quantity, which is a very simple operation. The next important operation actually is the dot product of a tensor with a vector. Like for example, how about if we do have the tau dot v? So tau it is a tensor, v it is a vector. How we can do so? We agreed through this course, like we're gonna use the Greek letter for the tensors, like tau, sigmas, mu's. These are the referred to a tensor, but the the English letter or the Latin letter like V, A, B, C, and so on, this letter in uppercase, this is gonna be referred to, this will be used for to refer or indicate a vector. So we do have a tensor dot vector, which is V. So let us write the tensor in its component form. So it's gonna be like tau ij delta I dot, there is a dot product here. We're gonna move to a vector, and this vector we have to use a different index. We already used the I and the j, so we have to use another index that we didn't use before because we're still working in the same term. So let us use k for example. Now we're just gonna do the multiplication, normal multiplication of the component. So we're gonna have the tau ij times vk, just normal multiplication, and then do the operation over the delta. So we're gonna have the delta I dot delta k. As we mentioned million times before, what is delta I dot delta k? We said that this gives us the canonical delta ij. This automatically gives us the delta ij, the canonical delta. So simply we're gonna say this gonna give us the tau ij vk delta ij. So how about if I would like to get rid of the delta ij? It means that you have to use the same index for both I and j. So what does it mean? I and j, they should have the same index. Let us assume that this index like I, for example. So I'm gonna say that tau I vk. As you can see, there is no deltas here. This is gonna give us a zero order tensor. So we're gonna end up with a scalar quantity. So the dot product of a tensor dot v dot a vector, this gives us the, no, I messed up here, I'm sorry, my bad. All right, so now let us move to the dot product of a tensor with a vector. Like let us assume that we do have tau dot v. So tau, this is a tensor, and v, this is a vector. We agreed that we are going to use the Greek letters for to refer to a tensor, like tau, mu, gamma. These letters are gonna be used for tensors, but we are going to use the Latin letters or English letter like A, B, C's and so on. These letters in uppercase to indicate a vector. So let us assume that we do have the dot product of a tensor dot vector. So to know what we're gonna end up with, let us write the tensor in terms of its components. So it's gonna be delta tau ij delta I delta j. It is second order tensor, so it has two unit vectors dot the v. For the v, we have to use a different index that we didn't use. Why? Because we're still working in the same term. So let us assume that we're gonna use k. We are not allowed to use either j or I for the vector because we're still working in the same term. So what we're gonna do is simply we're just gonna do the multiplication, normal multiplication of the components of the vector and the components of the tensor. So we're gonna end up with the tau ij vk. Just normal multiplication of this component. Then we're gonna end up with delta I delta j dot delta k. This operation should be done, the operation itself should be done over the unit vector. If you just compare, if you memorize, if you remember, this is what we discussed above a little bit with the operations over the unit vectors, and we said that to do it basically the single dot product, it should be done over these two. It should be done over these two unit vectors, right? And we're just gonna carry on the delta I as it is. This automatically gonna give us the delta j delta k gives us delta jk, the canonical delta. So what does it mean? It means that we're gonna end up with this relation, that this equals the tau ij vk, this term still the same, delta I, then we do have the delta jk. To get rid of the delta gk, the canonical delta, you have to use the same index for both j and k. So let us use j, for example, for both j and k. So we're gonna end up with tau I j vj, right? I'm just gonna use the same index for both the j and the k and delta I. And then you can cancel the canonical delta, which is the delta gk. So we're gonna end up with a vector. As you can see, we end up with a vector, right? Delta I just one unit vector, so it means that the dot product of a tensor, dot vector gives a unit, gives a vector. So we're gonna end up with a vector at the end. Make sense? If I ask you to, how about if we are interested in the expanded form? Vector, it means that we're gonna end up with 3 terms, right? Vector, it should have just 3 terms. This is the first term, like delta x, plus the second term, delta y times delta y, plus the third term, which is going to be times delta z. How about the first term? For the first term, as you can see here, inside the term itself, the j, it is a dummy index. So what does it mean, a dummy index? It means that it should be repeated. J, it should take x once, y once, and z once. It means that we're gonna end up inside one single bracket. Each single bracket, we're gonna end up with the sum of 3 different terms. So for example, here, it is already x. In the first x component, I is already x, right? Delta I is x. So it means that I already have tau x, and there is something here times v, right? So then you are going to repeat over j. J, it should be first x, vx plus tau x, I is already x, but j now it's gonna be y, vy, plus tau is already, I is already x, but the j, it should be z, vz. You got it? So I'm repeating the index x, y, and z over the j index, but I'm just gonna use I equals x in the first term. Why? Because the delta x is already, the delta is already delta x. How about the second term? Now I'm gonna repeat the same, but the only difference that the x, the first index in the tau, it should be y instead of x. So you're gonna have here tau y x vx plus the tau y y vy plus the tau y z vz. How about the z component? Is going to be the tau. Here the I should be z, and the j should be x, vx, plus the tau zy, vy, plus the tau zz, vz. Make sense? So these are the expanded, this is the expanded form of the compact form, which is given up there for the dot product of a tensor with a vector. Make sense? Now let us move to the cross product of a tensor with a vector. Cross product of a tensor, like let us assume that we do have a tensor tau cross product v. So what we're gonna end up with, I'm expecting that we're gonna end up with a tensor, but let us prove this thing. So for the tau in terms of the tensor, in terms of its components, is gonna be tau ij, delta I, delta j, cross product of the vector, which it should be like vk delta k. Remember, you have to use a different index. Then what we're gonna do, just do the multiplication over the components. So we're gonna have the tau ij vk, then do the operation itself over the vector. So we're gonna have here delta I delta j cross the delta k, right? And if you remember, as we discussed above, that this should give us, we're gonna do the operation over these two unit vectors. So, and this term should give us the epsilon jk l or m. Let us use m, for example, delta m. I have to use an index that I didn't use before, right? So this is gonna give us at the end, we're gonna end up with this form, like we're gonna have the tau ij vk. These are the components of the something that is going to be obtained, which we have no clue of what we're gonna obtain at the end, but we're gonna have here delta I, then we do have the epsilon jkm delta m, right? This epsilon, it can be included into the component part. So we're gonna end up with tau ij. We can even start with the epsilon or just keep the epsilon at the last term, but it doesn't matter. Let us start with the epsilon, like epsilon j km tau ij vk. As we agreed before, that it doesn't matter which one comes first. The order of these terms, it doesn't matter. Anyway, they're gonna multiply together and we're gonna end up with a tensor, delta I, delta m. So these two unit vector indicate a second order tensor, which mean that the cross product of a tensor cross a vector gives a tensor, a second order tensor at the end. How about if we decided to get rid of the epsilon? Or how about if I decided to write, because normally we represent a tensor as ij, right? This is what we already using a lot. How about if you decided to replace or use another index instead of m, like j, for example? So if to do so, it means that if I decided to use here j, so this m, it should be j, and this j should be used another index. You have to use another index for the j, like m, for example. Okay, and the same thing here, I'm gonna use m. So it doesn't matter which, you can just keep it as it is, or you just can play with the indices the way that you want. It doesn't matter. All the cases gonna give the same tensor at the end. So let us keep it, or just carry on and keep the tensor as we already got it here. How about if I decided to get rid of the epsilon? To remove the epsilon, so it should be split into like two indices, right? It should be split like into two different terms. So I'm gonna have here one term like delta I, delta m. Delta I, delta m. So the delta m, I'm gonna use the delta m. It means that I'm gonna do the switch between the j and the k only. And the I, it should be I as it is, because I'm using it outside. So it means that I'm gonna get rid of the epsilon. So I'm gonna end up with just tau and v. Negative tau and v, right? So, but how about the indices? The I, it should be the same. The I, it should be the same because I'm using it outside, right, as a common factor. But how about the j and the jkm? M, it should be the same. So the j, means that I'm going to play or just use the j and the k like as they already given here, then I'm gonna switch on the other side. So it means that j, it should be the same, k, it should be the same as it was shown here in this term. Then I'm going to switch positions, like instead of having j here, instead I'm gonna use the k here and the j with the v. So this is the expanded form, another expanded form, that in case that we decided to get rid of the epsilon that is already given up there. Make sense? So this is for the cross product of a tensor with a vector. The next operation is single product of two tensors. Like let us assume that we do have one tensor, two tensors, like tensor sigma dot tau. So this is a single dot product of two tensors. So what we're gonna end up with, let us figure it out and expand or rewrite again these tensors with their components in terms of their components. Like sigma, it's gonna be sigma ij delta I delta j dot the tau, which it should be the tau j. I'm sorry, I already used the I and the j, so I have to use two different indices like kl, for example, delta k delta l. Make sense? Just use any other two indices that you didn't use because we're still working in the same term. So now let us do the multiplication of the components kl, sigma ij tau kl, and let us do the operation itself over the unit vectors delta I delta j. These are the first two unit vectors. Then we do have a dot product here delta k delta l. If you remember that we considered a similar case before for the operations over the unit vector, and we said that this operation, it should be done just over these two unit vectors, right? And these two unit vector, their multiplication, the dot product gonna give us delta jk. Agree? This is gonna give us delta jk. So what we're gonna do, we're gonna end up with sigma ij tau kl. These are the components. Then we're gonna have here delta I, delta L, and there is delta jk as a canonical delta. If we decided to get rid of the delta jk, it means that we have to use the same index for both j and k. If we did so, basically we're gonna end up with sigma ij tau jl, where I decided to use the same index for both as j. So we're gonna end up with delta I, delta L. So again, this is gonna give us a tensor because this is a second order tensor. So the single dot product of two tensors gives a tensor. It makes sense? What next is double dot product of two tensors. So let us assume that we do have the double dot product of two tensors like sigma double dot tau. So for the double dot, basically it should be done over the unit vectors. So just represent the tensors in terms of their components. So we're gonna have the sigma ij, delta I, delta j. Then we do have the double dot operation, and we do have the tau kl, delta k, delta l. Make sense? Then we're just gonna do the multiplication of the normal multiplication of the components of the tensors in this way, and the operation, it should be done delta I, delta j, double dot product of delta k times delta k, delta l, right? As we agreed and we discussed in the operations over unit vector that this dot product is gonna give a dot product of these two unit vectors times the dot product of these two unit vectors, right? So we're gonna end up with something in this form. So we're gonna have the sigma ij tau kl, and we're gonna have here the delta j dot delta k times the delta I dot delta l. This gives us the first term sigma ij tau kl. The first term gives delta jk, right? And the second term gives the delta il. So to get rid of these deltas, it means that we have to use the same index for both j and k and the same index for both I and n. So what does it mean? It means that we're gonna end up with a tensor. Like, let us assume that we're gonna use j for both j and k. So we're gonna have here sigma I j tau j, and the l I'm gonna use I. You got it? Like, I'm gonna use for both j and k j, and for both I and l I'm gonna use I. So l should be I, k should be j. So we're gonna end up with this one. This is gonna give us the double dot product of two tensors. Is gonna end up with this form. Okay, and as you can see, we end up with a scalar. There is no vectors. It means that the dot product, the double dot product of two tensors gives a scalar quantity. Okay, the next thing, so these are the most common operation that would be done over tensors, like the dot product of a tensor, single dot product with a vector, single dot product of two tensors, double dot product of two tensors, and even with the multiplication by scalar value. Now let us move to other three main parts here, or two main parts basically: the transpose of a tensor and the symmetric and skew-symmetric parts of a tensor. Then we're gonna end up with the trace of a tensor. What is the transpose of a tensor? The transpose, it is very simple, very similar to the matrix. It's just to replace positions between columns and rows. Like, you're just gonna switch the row to be column and the column to be row, which is very simple. So how we can represent this tensor in terms of the tensor notations or tensor calculus? So basically we represent, like, let us assume that we have a tensor tau, And if we just add a superscript here, T, this indicates that this is a transpose of this tensor. So we're gonna say that what is the transpose of the tensor? To represent this thing, basically let us represent the tensor in terms of its component, like tau ij, delta I, delta j. These are the components, and we are interested in the transpose of this tensor. So simply the transpose, just switch column and position, the position between column and rows, but the unit vector, they should be still the same. So what does it mean? It means that I won't gonna switch the indices over the unit vector, but I'm just gonna do the switching over the indices of the components themselves. And I'm just gonna keep the unit vector, they are the same as were given for the original tensor. Like for example, I'm gonna say that this transpose is gonna make me switch positions between I and j over the components only, but the delta I, delta j, they should be the same arrangement as they were given in the original tensor. Make sense? So this is how we can represent the transpose. Simply, the transpose is just doing swapping over the components or the indices of the components, but there is no swapping over the unit vectors. Make sense? How about the symmetric and skew-symmetric tensor? As we discussed above, that the tensor in general, it has 9 independent components. Like any tensor, if we are going to represent it generally in the tensorial form, this is a tensor. So this tensor will have a diagonal, some 3 components. If we're going to talk about the 3 by 3 tensor, which the second, like 3 by 3 matrix, which is the second order tensor. So for the second order tensor, we're going to have 3 components located over the diagonal, right? And also we're going to have three other components which are located at the outside the diagonal. These components that located outside the diagonal, they are known as the off-diagonal components. So these are the off-diagonal components, the off-diagonal components. Okay, these are the off-diagonal components, but these are the diagonal components. Make sense? This is generally for any tensor, whatever it is, second order tensor, third order tensor, but for the commonly used one for linear elasticity, the second order tensor, we're going to have 3 components over the diagonal and 3 other components on the upper part of the off diagonal, and 3 other components over the lower part of the off diagonal part. So we have here 3 components, and we do have here 3 components, and we do have 3 other components, right? So in total, we do have 9 components for any 9 components for a second order tensor, and this is basically what we discussed before. But this tensor, basically, it can be decomposed into 2 parts, into 2 tensors. Just the second, here we are talking about the second order tensor. It can be decomposed into 2 components. It can be decomposed, or like kind of divided into symmetric part and skew-symmetric part. What is the skew-symmetric part? The symmetric and the skew-symmetric parts, these are like 2 other tensors. Like I can decompose this general, this is known as the general tensor. This is known as a general tensor that has, this is the general tensor that has 9 independent components. What does it mean, independent components? It means that all the components, they should be kind of different in the most general case. But anyway, it has 9 components. I can decompose this one or divide this tensor into 2 other tensor that can be derived from the general tensor. These other tensor, one is a symmetrical tensor or a symmetric tensor, the second one is a skew-symmetric tensor. So what is the symmetric and what is the skew-symmetric tensor? The properties of a symmetric tensor that it is the tensor whose components or whose off-diagonal components are identical. This is going to give us the symmetric part of the tensor. So we're going to say that in case, so the symmetric tensor. For the symmetric tensor, you should understand that the tau ij, it should equal to the tau ji. And this is basically what was mentioned to you for the mathematics class, that the symmetric matrix equals its transpose. Because if you just flip or switch positions between the two indices like tau ij or tau gi, because when we switch indices over the component, this gives us the transpose as we discussed above here, right? So it means that the symmetric tensor is typically equal its transpose. So in case that we have this tensor with this characteristic, we're going to say that this tensor is a symmetric tensor. On the other hand, the skew-symmetric tensor, the skew-symmetric tensor, it is not common basically, especially in the field of linear elasticity. We are depending a lot on the symmetric tensor, as it's gonna be clear as when we discuss the stresses and the strain, the stress and the strain tensors. But anyway, the skew-symmetric tensor, it had this property that the tau ij equals the negative of tau ji. Like if you try to find the transpose, you're gonna end up with, like, you already multiply the tensor times -1, and in the meanwhile its components, its diagonal components are zeros. You should understand that the skew-symmetric tensor has 0 diagonal components. But the symmetric tensor, it would have any components over the diagonal, but the off-diagonal parts, they should be identical. But for example, if the off-diagonal parts here, they are the negatives of the off-diagonal components here, and the components of the diagonal are zeros, this gives us the skew-symmetric part of a tensor. This indicates a skew-symmetric tensor. Like for example, let us consider these examples. How about if we do have, as an example here, how about if we do have this tensor tau equals, and let us just give some numbers like 1, 4, 5, and there is here 6, 2, 7, 0, -1, and 3. And let us consider another tensor like sigma. For example, sigma with 5, 4, 1, and we do have here 4, -1, -2, and there should be here 1, and we do have here a -2, and there is 0. And how about if we do have gamma, which is another third tensor, with these values or these components, like we do have here 0, -1, 2, and we do have 1, 0, -5, and we do have here -2 and 5 and 0. So according to the previous definitions, the tensor tau, it should be a general tensor. Why? It has diagonal components. These are the diagonal components, right? These are the diagonal components, and it has off-diagonal components here, 3 diagonal components, and there are 3 other diagonal components. These components are not identical, even they don't have the same value, but different signs. They totally different in terms of value, in terms of sign even. So like here we do have 4, but here we do have 6. Here we do have 5, we do have here 0. 7, -1. So these components they are not identical. So it means that this should be a general tensor. But how about this one? This should be symmetrical tensor. Why? It has off-diagonal components. Even though off-diagonal would be 0, and still we're gonna end up with a symmetric tensor. But the key point of the symmetric tensor that the off-diagonal components, they should be identical. Like this 4 is identical to this 4. Like this is the xy position. Here we have the yx position. So that's why we say that the tau xy, it should equal to the tau yx for this tensor to be symmetric. And also here, this is the xz position, right? Xz position, and this is the zx position. So it means that the tau, or here, I'm sorry, we are talking about sigma. The tensor is sigma in this case. So we're gonna say that the sigma xy, it is equal to the sigma yx. Here also the z component, the zx component, this is the zx component, and this is the xz component. And this is the zx component, they are identical. It means that the sigma xz component should equal to the sigma zx component. And we do have here, this component is identical to this component. This is the yz component and the zy component, they are identical. It means that the sigma yz is equal to the sigma zy, which indicate that we do have, it means that if we decided to write this one in the compact form, so we're going to say that we do have the sigma ij, it should equal to the sigma ji. Make sense? And this what defines a symmetric tensor. It means that this should be the symmetric tensor. Make sense? How about this one? This one, it should be skew-symmetric tensor. How? The diagonal is zeros. The diagonal components, all of them are zeros. And if you just observe this term and this term, you're gonna find that the xy equal the negative of yx, or the yx equal the negative of the xy. It means that the sigma xy equal the negative of the sigma yx. And if you compare this term to this term as well, so you're gonna find that the sigma, or the gamma, should be gamma. This is the gamma xy, it should equal to the negative of gamma yx. And if you compare this term to this term, you're gonna end up that the gamma xz, it should equal to the negative gamma zx. And if you compare this term to this term, you're gonna find that the gamma yz equal the gamma zy. This indicates that this tensor gamma ij equal the negative of gamma ji. It means that if you try to find the transpose, switch the indices, switch position, you should multiply times -1, and the gamma rr, it should be 0. So what does it mean the gamma rr should be 0? This refers to the trace, to the diagonal. This is the trace known as the trace of the tensor. What is the trace of the tensor? This just you gonna collect the components over the diagonal, it should be 0. Like the tau rr, it means that the r, it is a dummy index, is going to be repeated. So we're gonna have like gamma xx, it should be 0. Gamma yy, it should be 0. This component is gamma yy, this is gamma xx, gamma zz, it should be 0. This is the meaning of that you do have a skew-symmetric tensor. So we're gonna say that this tensor is a skew-symmetric tensor. Make sense? So we knew how we can do transpose for a tensor. Then we discussed the symmetric and the skew-symmetric parts, that we said that the tensor, it would be composed into symmetric and the skew-symmetric parts. And we defined, for now we distinguish between these symmetric and skew-symmetric tensors in general. But how we can obtain the skew-symmetric and skew-symmetric parts? As I mentioned above, that any tensor, any general tensor, it can be decomposed, like any tau in general, it can be decomposed into symmetric part I delta j, there is no dot here, plus another skew-symmetric part, which is still tau I j delta I delta j. So what is this form? What is this parenthesis? Why did we add here parentheses? These parentheses refer that we are talking about the symmetric tensor or the symmetric part of the overall tensor. This is the general tensor that has been decomposed or divided or split into symmetric part and the skew-symmetric part. This is the skew-symmetric part. Make sense? So what does it mean? It means that we are going to use the parentheses to refer to the symmetric part of a tensor and the square brackets to refer to the skew-symmetric part of the same tensor. Make sense? We can even, there are different ways actually to represent. We can even represent this one just took like tau s, where s stands for symmetric, and this like tau k, where k stands for the skew-symmetric part of the tensor. Whatever, it doesn't matter. You should understand that the general tensor, it can be decomposed into symmetric and the skew-symmetric parts. The question is how we can obtain the symmetric or the skew-symmetric part of a tensor, like the tau symmetric of a tensor. It should be the tau ij symmetric of the same tensor, and this it can be obtained by half of the tau ij plus the tau ji delta j. So what does it mean? It means that you're just gonna add the transpose, the tensor to its transpose to end up with its symmetric. If you added the tensor to its transpose, if you sum them together, and we discussed above how we can add two tensors together. If you just add the components together and take half of them, like you are already taking the average of these components, you're gonna end up with the symmetric part of the general tensor. But how about the skew-symmetric part? It is simply half the difference between the tau ij negative the tau ji. You're just gonna switch here and take a negative delta I delta j. This is gonna give us the skew-symmetric part of a general tensor. Okay, we're gonna consider an example here. Okay, so let us consider this example here. Example. It is required to find the tau symmetric and tau skew-symmetric. Mean that we are interested in the symmetric and the skew-symmetric parts of tensor tau, which is already given in this form as tau given by 1, 2, -1, and we do have -1, 4, and 0, and 5, 4, and -3. Make sense? So simply, as we demonstrated above, that the symmetric tensor, it should be half the tensor itself plus its transpose. Like you just gonna add the tensor to its transpose, but you're just gonna multiply times half. So what are the components half? What are the components of this tau? It should be the tau ij delta I delta j plus, how about the transpose of the same tensor? You're just gonna flip these components, like still if having ij, so you're gonna have ji, but you're just gonna still keep the unit vectors the same. So you're gonna end up with delta half. Then we can consider the delta ij as a common vector, so we're gonna end up with the tau ij plus the tau ji delta j, right? And this is what we already wrote above for as a definition of the symmetric component or the symmetric part of the general tensor tau, right? So what does it mean this? It means, for example, if I ask you to write this thing in an expanded form, what is the expanded form? This is gonna give us a tensor, right? But this tensor tau, let us write this tensor in an expanded form or a tensorial form. So it's gonna be half. We can consider this half as a common factor, right? And we're gonna have here this tensor. little bit big tensor. So, and we're gonna have here the x components. This is the x column, the y column, and the z column, and the x row, the y row, and the 0. Make sense? So this component here, it should be xx. It means that I and j both are x. So we're gonna end up with tau xx plus tau xx. Make sense? How about the y component, the yx component? This component should be yx. It means that the j, it should be y, because this is the column, and the I should be x. So we're gonna have the tau xy plus the tau yx. How about the z? So it's gonna be the tau, the z is the column, so the j, it's gonna be z, the I should be x, so it's gonna be xz plus the tau zx. Make sense? And so on. So here we're gonna have the tau yx plus the tau xy, and tau yy plus the tau yy. Here we're gonna end up with the tau z, this is gonna be yz plus the tau zy, and here we're gonna have the tau zx plus the tau xz, and here we're gonna have the tau yz, y plus the tau yz, and here we're gonna have the tau zz plus the tau zz. So as you can see that this tensor, if we're gonna end up with this tensor in this form, that this component here is typically identical to this one. It doesn't matter which comes first, like tau xy plus tau yx is typically equal to tau yx plus tau xy, right? The same thing, this component is identical to this component. This component is identical to this component, right? And then we do have the off-diagonal component, which it should be double the tau xx, double the tau yy, double the tau zz, but you should remember that there is half already outside here, right? So, and this is typically the characteristics of the symmetric tensor, that the off-diagonal components should be identical, right? And this is what we already got in this case, right? So simply, to find these components, your objective is just to sum these different components. Like, for example, to find the tau xy and the tau yx plus tau yx, it means that we have to sum 2 plus -1, which is going to give us 1. So we're just going to add here 1 and 1. This is going to give us these two components automatically. You got my point? So let us do it here. For example, if we decided to do it for this tensor, we're gonna end up that the tau symmetric, it should be the half of this tensor. So as you can see, for example, you're just gonna double the diagonal components, right? We already doubled here the diagonal component. Or even if you decided to multiply times half inside, let us multiply the times half inside automatically. So this means here we're gonna end up with 2xx times half. This is gonna give us only 1 tau xx, right? So it means that we're just gonna carry on. We're just gonna copy the diagonal components as they are. We won't gonna do any changes, and we're just gonna put them over the diagonal here. So we're gonna do the same. It means that these diagonal components are 1, 4, -3. So we're gonna have over the diagonal components 1, 4, -3. How about the off-diagonal component? There should be one component here, one component here, one here. These are the 3 off-diagonal components. So let us start with this component, this one. Okay, this one, it should be the tau xy plus the tau yx. It means that we're just gonna sum these two terms together. So 2 plus -1, this gives 1, and there should be half here, right? There should be half. So we're gonna end up with 1/2, half, 1/2, and there should be 1/2 identical, two identical terms. How about the tau xz plus tau yz? You're just gonna sum these two terms, -1 plus 5. This is gonna give us 4/2, because there is a half, so we're gonna end up with 2, and there should be 2 here. How about this component? This should be tau yz plus tau zy, tau yz, which is 0, plus tau zy, which is 4. So this is going to give us 4 over 2. This gives 2. So this is going to give us the symmetric part of this tensor that we have. How about the skew-symmetric tensor? The skew-symmetric, it should be half the tau negative its transpose. Negative its transpose. So this is going to give us half of the tau ij delta j negative the tau ji delta j. Remember that we're just going to keep the unit vector, but we're just going to switch over the component themselves. So we're going to end up with half of the tau ij negative the tau ji, and we're just going to consider the delta I delta j as a common factor. So this is going to give us a tensor. This tensor tau k in the tensorial form is going to be, if we decided to take the consider the half as a common factor, so we're going to have here the tau xx negative tau xx. Just what we just going to do, replace this sign in the middle, instead of being positive to be negative sign. So we're going to end up with these terms like tau xy negative tau yx and tau xz negative tau zy, then zx, I'm sorry, zx. Then we're going to have here the tau yx negative tau xy. Here we're going to have the tau yy negative tau yy, and we're going to have the tau, this should be the y, the row yz negative tau zy, and we're going to have here the tau zx negative the tau xz, and we're going to have the tau zy negative the tau yz, and tau zz negative tau zz. This is going to give us the skew-symmetric tensor. It is clear that all the diagonal components of the skew-symmetric tensor are zeros, because tau xx negative tau xx equals 0, this one equals 0, this term equals 0. So that's why we said that for the skew-symmetric tensor it has 0 diagonal components and it has only off-diagonal components. And as you can see that this term, it is the negative of this term, because we switch position, right? The same thing, this term, it is the negative of this term. This term, it is the negative of this term. And this is what defines a skew-symmetric tensor. So what does it mean? It means that at the end, the skew-symmetric tensor, here, tau k, it's going to be half, we're just going to multiply the half time the tensor. So the diagonal should be zeros, as we agreed, right? But how about the tau xy negative tau yx? Tau xy in the original tensor, the general tensor, it is 2 negative 1, this gives 3 over 2, this gives 1.5. So this is going to give us 1.5 here. How about this one, tau xz negative tau zx? Tau xz, it is given by negative 1, negative 5, this is going to give us negative 6, negative 6 over 2 gives negative 3. So it's going to be minus 3. Intuitively, if we repeat it, as we mentioned, this term is the negative of this term. So since this term is already 1.5, this term it should be negative 1.5 intuitively, right? So automatically, we're going to have here negative 1.5. This term also is going to be just 3. We still have only one term, which is the tau yz negative tau zy, tau yz, which is this one, 0 negative tau zy, which is 4. So it's going to be negative 4 over 2 gives negative 2. So we're going to end up with a negative 2 here. Then this negative 2, it should be 2 here, right? So this is going to give us the skew-symmetric bar. To make sure that what we did is correct, or we are in a good shape, if we try to sum the tau s plus the tau skew-symmetric, the symmetric tensor, plus the skew-symmetric tensor, we should end up with the original tensor back again. We're going to get the original tensor back again. If you try this one, just sum this tensor to this tensor, you're going to find that typically we're going to end up with the general tensor. Make sense? This is for the skew-symmetric and symmetric parts of a tensor. The last thing that we're gonna discuss here is the trace of the tensor as we quickly discuss this thing. The trace of a tensor simply it means that we are collecting the diagonal components of a tensor and we sum these diagonal components, especially if we're going to talk about second order tensor. Like you do have, these are the diagonal components of the tensor, like we do have tau xx, we do have tau yy, and we do have the tau zz for a specific tensor, tau. So the trace of the tensor basically it is written as tr, which stands for the trace of tau. This typically can be written in terms of the components as tau rr or tau ii or whatever. I mean, like you just gonna use the same index and you just gonna repeat it, which is like tau mm. So this is the trace. And if I ask you to expand, this is the compact form, to expand this term, it means that R is a dummy index, so it should be repeated. So it's gonna be like the tau xx plus the tau yy plus the tau zz. So simply the trace of a tensor, you're just gonna collect the diagonal components of this tensor, sum them together, you're gonna end up with the trace of this tensor. Okay, and if you sum them together, in many of the cases, the trace of this tensor, it should give us like, it would be considered a tensor. Generally, we're gonna consider like, because there should be, if this is the tensor, there should be like delta I, delta j, the unit vectors here, and there should be delta I, delta j, and there should be delta I, delta j. But for this one, these components will be eliminated because here we are collecting this trace. So in many of the cases, the trace is a scalar quantity that that represents the sum of the diagonal components of a certain tensor. But it would by itself indicates a vector or indicates a tensor, but here we are talking about the trace tensor, which would be confusing. But anyway, let us, for now, the tracer is the sum of tau xx plus tau zz plus tau yy, and we can consider this generally as a tensor. So for example, here I'm talking about that the trace of this tensor, it should be like, let us consider this example is going to be clear. If we do have this tensor tau, like 1, 2, 4, 5, 3, 0, 0, negative 1, 6, for example. So this is a general tensor. And how about if we are interested in the trace of this tensor? So the trace of the tensor tau, it should be the tau ij, delta I, delta j. This is the tensor in terms of its component, and we are interested in the trace of this tensor. So the trace, it should give us the tau, it should give us the 1/3 of the tau rr delta I delta j. Why we are divided by 1/3 here? Because we are going to collect these three terms together. So we gonna end up, it means that we just gonna take the average of these diagonal components and we are going to distribute them over these over the diagonal. So it's gonna be just here delta I delta j, delta I delta I. It should be the same index because we are going to distribute over the diagonal. So this tensor, the trace of this tensor, it should be, what you're gonna do simply just sum the diagonal components, these three components. So 1 plus 2 plus 3 gives 6, divided by 3 gives 2. So we're gonna have here 2 and 2 and 2 over the diagonal and zeros everywhere. You got it? So this is gonna give us the trace. This represents the trace of this tensor tau. So simply the trace, it means that we are talking about the diagonal component themselves. And in many of the cases, we are going to subtract, to add them together. And here we are dividing by 3 because these components will be summed. Then we have, like, we're already taking their average of these three components over the trace. But anyway, for now, just get understand it in this form, in this way, As the trace, we are talking about the diagonal, and we are going to sum the diagonal somehow of this component of the diagonal somehow. Okay, and so that's it for the operations over the tensor. The next video we are going to talk about the differentiation or the differential operations that would be done over vectors and tensor, and by the next video is going to be the last topic for the tensor and vector calculus. Thank you.